Hi everybody. I will be talking to you about adding, subtracting, multiplying, and dividing radical expressions. So basically basic operations with radical expressions. Now if we remember, radicals can be rewritten as rational exponents. So this brings in something that we need to talk about when it comes to simplifying, because as we do these basic operations, we will need to consider simplifying, specifically when it comes to multiplying and dividing. So what happens is we do not deal with imaginary numbers in Algebra 2 when it comes to radicals. We know that we drilled this when we were talking about solving for quadratics and solving for polynomials, but we do not dive into the imaginary numbers when it comes to radicals. So what do we do when we encounter an even radical? Now, a recap on some vocabulary words. The n that's in here is called the index. If the index is even, then we need to consider making sure that nothing inside will ever be negative. And the way that we do that is through these absolute value bars. Because if we end up having absolute value bars, that means that that value is always positive. Another vocabulary term, the inside stuff, is called the radicand. We will visit that in a few of these examples, but essentially the number in the elbow is considered the index, and all of the information under the radical is called the radicand. So let's take a second and rewrite number 1 as a rational exponent. So this came from an even index, but the exponent is even, which means that no matter what, this value is always going to be positive. So we do not need absolute value bars here. Let's work on number 2. Number 2, let's rewrite. So now for this one, because x to the 5th is potentially going to result in something that could be negative, there's no way that the original problem could have been negative. So that's why we do the absolute value bars. We want to maintain balance in math. If we started with something that can only result in positive answers, we want the simplified version to also have that. That is why we utilize our absolute value bars. It is also links back to the issues with your imaginary numbers. Okay, let's do one that's a little bit more complex. So this is going to take some thinking back to Algebra 1 skills to simplify this. Algebra 1 really only focused on simplifying square roots. So for this one, we are working with a 6th root. So for the number 192, we do want to consider thinking about that over here as a factor tree and breaking this guy down. So take a second, break 192 down into your factor tree. Okay, so once you've broken down 192 into your factor tree, when we were working with square roots, we would look for groups of 2. For this one, we look for groups of 6. But I'm going to take a second sort of and do an in-between step here. So I'm just going to write the prime factorization of 192 under this 6th root. If you need to, one of the ways to work through this is changing all of these to a fractional exponent. If it is easier for you to do that, please feel free to do that. I'm going to show you how that works. If you can see how to do this, how to simplify this without having to change it to fractional exponents, that is also fine. Just know that when we start our problem with a radical, we should end, our final answer should be with a radical. So if you change it mid-problem to fractional exponents, please make sure your final answer is in radical form. Now don't simplify any of these in the concept of, like, you know, how 14/6 can simplify to 7/2, or sorry, 7/3. Don't do that. Not until the very last step, if necessary, because you do want to keep the denominators the same to rewrite it in radical form. So 2 to the 6/6 actually ends up changing into 2 to the 1st, which means that this guy is going to end up popping outside of the radical, coming outside of the radical. 3 to the 1/6 is going to stay 3 to the 1/6. We can't simplify that any further. X to the 19/6. We want to think about this improper fraction as a mixed number for a second. So I could have this be 3 and 1/6, because that would be 18/6 plus 1/6. So the idea behind this is, if you think about it as a mixed number, the x to the third, or the 3 and 1/6, the x to the third would break off of that, and that would be something that would come outside the radical. And then you'd end up with x to the 1/6. That means that that would stay inside the radical as a part of the radicand. Similarly, z to the 14/6, we can think about that as a mixed number of 2 and 2/6. So that would mean that z squared would be the item that would come out, and then z to the 2/6, that would be the element that would stay inside. So how does this translate back to a radical? All of the purple would be what would come outside. So we have an x to the third, a z squared, and then inside the radical, this is a 6th root. Please don't forget your index. We have 1, 3 to the power of 1 inside. We have x to the power of 1 inside. And we have z squared inside. Now remember, I said denominators need to all be the same because they should be all going under the same radical. You do not have to split this into 2 separate radicals. 2/6 could simplify into 1/3, but we want to try to make this as easy as possible. The one last thing for this one is we did start with an even index. So in order to compensate for negatives and i's, we need to consider, did we take anything out that has an odd exponent? And we did. This x to the third is an odd exponent, so this would go in absolute values. Even though 2 is to the first power, 2 is a number, 2 is positive, we don't need to put that in absolute values. Z squared should not be put in the absolute value bars. So this is the most simplified version of number 3. Okay, let's add on to that. Products means that as long as their indexes are the same, you're allowed to multiply the radicands, the insides. So very similar to what we just did, except for there's a step prior to. We make sure the indexes are the same, multiply the radicands inside, multiply the coefficients on the outside, and then simplify just like we did with number 3. So on the outside, we just have a 2, so we are going to have a 2 here. This is an index of 3, so we do need to make sure that we have the index of 3 on the inside. So we have the 5 times the 50. 5 times 50 is 250. Y cubed times y to the 4th. Remember, we add exponents. Our laws of exponents apply here. So that means that we have y to the 7th. So now we have to simplify this just like we did the last problem. So take a second, do your factor tree for 250, and then simplify from there. I'm not going to rewrite this in fractional exponents. I just did that for number 3 so that you guys could see an alternative way to do this. So we have 5 to the third inside, so this would be 5 to the 3/3, which means 5 would come outside. We have a 2 to the first, which means the 2 would be inside. We have a y to the 7th, so that would be y to the 7/3. There are 2 sets of y's that would be able to fit. So the mixed number would be 2 and 1/7, which means y squared would come out. So what's left inside would be, we said 2 to the 1st would be left inside, and 1y would be left inside as well. Now we do not need to consider absolute values because we came from an odd index. Odd radicals can work with negative numbers. That is okay. So we don't need that absolute value idea for this. So the final simplified answer for this one would be 10y squared cube root of 2y. So what happens if the indexes are not the same? We do need to take a second and rewrite everything in fractional exponents. So break down 40, break down 32, rewrite everything with fractional exponents. Okay, this would be rewritten like this. So we do need to consider common denominators for this. We need to apply our laws of exponents. We have like terms with the bases of 2. So we do need to make sure that we find common denominators for those. We are going to want to put this under one radical at the very end of everything. So we do want to make sure that everything has a common denominator. So we have 3's and 4's, which means our common denominator will be 12. So take a second, see if you can simplify this using your laws of exponents. Find everything with a common denominator of 12. Common denominators of 12s, as you can see, we add the exponents with the bases of 2 together. So 2 is the only one that we need to consider simplifying a little bit to get on the outside of the radical. Everything else is on the inside of the radical. So 29 12s, how can we think of that as a mixed number? It would be 2 and 5 12ths, which means 2 squared would end up on the outside of this radical, and 2 to the 5th would end up inside this radical. So we do have an index of 12, so we need to make sure we put a 12 in that elbow. So take one more step and simplify your numbers. We know what 2 squared is. Figure out what 2 to the 5th is. Make sure you're multiplying that with 5 to the 3rd. It is going to be a larger number, but that is okay. And then that would be your final answer. This is an even index, but we did not have any variables that simplified to the outside of this, so absolute values are not necessary for this answer. Division is the same. Indexes should be the same. If they are, we can take the insides, the indexes, and divide them, simplify them. If when we simplify there are radicals left in the denominator, we do need to consider rationalizing, because remember, we don't like radicals in the denominator. Radicals are fractional exponents. We had practice rationalizing the denominator. When it came to fractional exponents, this is no different. So the indexes are the same. They are even, so we do need to make sure we're considering absolute values, but we'll talk about that at the end. So we do want to consider throwing these under one radical. We do have the 10 and the 2, so we do want to consider the 10 and the 2 and simplify those on the outside, but then everything else is in this radical. We want to take a second and utilize some laws of exponents and simplify. Remember, when we have division, that means we're subtracting exponents. So this 10 over 2 simplifies to 5 over 1. So now we want to rewrite these as 2 separate radicals again. So we do have a radical in the bottom. We need to fix that. Keep in mind, 4 can be written as 2 squared. So we do want to consider how are we going to rationalize this. Remember from your rationalizing with fractional exponents that 2 squared under a 4th root is 2 to the 2 fourths. how do we make 2 to the 2 fourths the next whole number? We would have to multiply this by 2 to the 2 fourths again, which means we're multiplying this by the fourth root of 2 squared. This is x to the 1/4. So how much are we multiplying to get that to the next whole number? It would have to be 3/4. So that means this would have to be x cubed in here. And what we do to the bottom in math, we do to the top for balance. So then after doing that for rationalizing, we have, now this is not quite done because we do have a y to the 5th in the top. Technically, that we can think about this as y to the 5/4. So this is 1 and 1/4. So the final simplified version of this, now we did come from a fourth root, which means that we do need to consider that any variable that's simplified to the outside of the radical that has an odd exponent needs absolute values. So the y is to the first, that needs absolute values, and the x is to the first, which means those need absolute values. And that is as simplified as that's going to get. Okay, let's talk real quickly about addition subtraction. So this one, these are pretty straightforward. These typically tend to be quick. We don't add, there aren't too many questions that we'll throw at you that have variables. It's mostly just numbers, but the goal is to simplify each term and then combine like terms. Now, what do we consider like terms? There's 2 criteria here. Like terms have to have the same index and the same radicand. So let's take a second on this last example, pause the video, simplify these as much as you possibly can. We have 2 cube roots and a square root, so take a second and simplify these as much as possible. So now that I've done the prime factorization, I just need to simplify it one step further. So now here is where we look for the indexes and the radicands. So the elbow number and the inside number. So the red and the green both have an index of 3, but do they have the same radicand? They do. They have a radicand of 2. So this idea is like thinking about, I have 6 of this item and 4 of the same item. How many of these items do I have together? I have 10 of them. So if we combine like terms, we have 10 cube root of 2 minus 12 square roots of 6. And those cannot be combined any further. Square root has an index of 2. Cube root has an index of 3. So that is as simplified as it is going to get.